Next, let's talk some more about energy storage in capacitors and electric field energy. We said the electric potential energy was stored in the electric field, so let's think about that a little bit more and let's relate the expression for the electric potential energy and the electric field. So we'll start with our previous result. UC is the electric potential energy stored in a capacitor, is equal to 1/2 times C times delta V squared. Okay, what are we going to do with this expression? Well, C is the capacitance. We know it depends on the physical properties of the capacitor. C equals epsilon naught times the area of the plates divided by the plate separation D. And the potential difference between the plates depends on the plate separation and the electric field. So the size of the potential difference is the size of the field times the plate separation. If we put this in here and this in here, then what we get for our expression for our electric potential energy is equal to 1/2 times epsilon naught A over D times the electric field squared times D squared. And then this boils down to 1/2 times epsilon naught times A times D times E squared. So this is the expression for the electric potential energy stored in a capacitor in a vacuum. So this expression is a vacuum. We'll just put a side note that if we had a dielectric, we would have to include our constant K. Or kappa, sorry, I said K because it looks like a K. And then we might remember that we can express kappa times epsilon naught as just plain old epsilon. Or just plain old epsilon. So the dielectric constant, kappa, times the permittivity of free space is just the permittivity of the material. Okay, so we don't want to forget about dielectrics altogether. Okay, let's come back to this expression. So we see that the electric potential energy definitely has a dependence on the electric field. Let's think about this part right here. We see A times D in our expression. What is A times D? Well, A times D, if our plate has area A, bear with me while I try and draw this in 3 dimensions. So there's our plate in 3 dimensions, and the bottom plate is 3 dimensions as well. So the plates have area A. I can shade that in, area A. The bottom plate has area A. The plates have separation D. So A times D, that's the volume of space between the 2 plates. That's an interesting result. The other thing is that the electric field goes from the positive to the negative between the plates of the capacitor. So A times D is the volume between the plates. That's the volume where the electric field is. So A times D equals volume between the plates which is where the electric field exists. So that's a pretty interesting result. So that tells us that the electric potential energy is stored in the electric field. So it depends on the strength of the field, and it happens in that area, in that volume where the field is. Okay, so now it can be a useful result to define what's called energy density, which is the energy divided by that volume. So let's define that term. So define energy density we're going to give energy density a symbol of a lowercase u with a subscript of E. I'm going to try and keep my uppercases and my lowercases sufficiently different so that you can tell what it is, and they also have different subscripts. So my energy density, UE, is going to be my energy divided by volume. Just like all densities, is something over volume. So my energy is my expression from energy up here, UC. So my electric potential energy of a capacitor divided by the volume, which is A times D. So I'll take my expression 1/2 times epsilon naught times AD times E squared, divide that by AD, and what I get from my result is that my energy density is equal to, so my AD's cancel, 1/2 times epsilon naught times E squared. I think this is actually a pretty interesting result. Now we use the expression for the electric potential energy with nothing between the plates, so this expression is for a vacuum. What kind of comments can we make about this? So this expression gives us the energy density in the electric field. It depends on the electric field and it depends on the permittivity of free space. You'll notice that this expression right here, it doesn't depend on the fact that we have a capacitor. So this expression is actually true for energy contained within any electric field. That's a pretty interesting result. And we see that energy gets discharged as the electric field collapses. This is another signal that the electric field, even though we can't see it, is actually a real thing. We can see that it stores energy. So the last thing we'll fill in here, if we didn't have a vacuum, if we had a dielectric between the plates, then the energy density, we'd have to include our dielectric constant kappa here. So you could write it just as this, or you could say that kappa times epsilon naught is epsilon, the permittivity of the material. So we see that something with a dielectric can store more energy, and that makes sense because there's an extra electric field inside the dielectric itself, and we saw that when we talked about dielectrics in that section. Let's do an example. So let's do an example of a device you may be familiar with. An AED has a defibrillator. I find this so hard to say. Defibrillator unit. And that has a capacitor that's charged at all times. So if somebody has a heart attack or some sort of abnormal heart rhythm, the heart goes into what's called fibrillation, and you get these random muscle twitches. When you put the paddles of an AED on someone's chest, it sends a shock through the body that stops the heart and lets it restart properly. So the capacitor in the AED is similar to the capacitor in your camera flash. It charges up slowly till it has an energy of about 360 joules, and then it releases real fast and sends that energy through in one quick burst. That's why in all the TV shows they yell clear just as they hit the handles so that nobody gets a shock from it. Okay, so our unit has a 150 microfarad capacitor. It's charged to 2100 volts, separated by a 0.05 millimeter thick dielectric, where the dielectric constant is 300. We want to find the total charge, the area of the plates, and the energy in the capacitor. Let's make a list of the things that we know. The capacitance is 150 microfarads, so 150 times 10 to the minus 6 farads. The potential across the plates of that capacitor when it's fully charged is 2100 volts. The plate spacing is 0.05 millimeters, so 0.05 times 10 to the minus 3 meters, and our dielectric constant is 300. Part A, we're asked for the magnitude of the net charge on the capacitor. So if we remember that our expression for capacitance, C, is Q over delta V, we can rearrange to find that Q is C times delta V. Plug in our C, plug in our delta V. That's a pretty high potential. And we get 0.315 coulombs. That is actually a lot of charge to have flowing through your body at one time. Part B, find the area of each capacitor plate. So if we just do a quick sketch of our plates, something like this. Separated by distance d, we want to find the area of the plates. So we know that capacitance is equal to, if we only had a vacuum, it would be epsilon naught A over D. We don't have just a vacuum. We have something in between those plates. We have a dielectric. So that area of space is filled up with a dielectric. And that means our capacitance is kappa times the capacitance of something that's only filled with a vacuum or empty space. So then the area of the plates is going to be D times the capacitance divided by kappa times epsilon naught. Fill in our D. Fill in our capacitance. Kappa is 300, and epsilon naught is our permittivity of free space, 8.85 times 10 to the minus 12 farads per meter. That gives us an area of the plates 2.82 meters squared. Okay, that's a pretty big area. If you were thinking about it, if your capacitor plates were square, they would be 1.7 meters on a side. People who think imperial versus metric, that's like 5.5 feet by 5.5 feet. If you spread out your arms, then the distance between your fingertips is probably a little bit close to 5.5 feet. Less for some people, more than other people. So that's a pretty darn big capacitor. You might try and pause and think, how on earth do they make a capacitor of that size to fit inside this device? If you can't get it, that's okay. I'll talk about it in a couple of minutes, but puzzle on it just for a moment while we finish the problem. Part C, what's the stored energy and what's the energy density in the electric field when our capacitor is fully charged? So our energy has the symbol of capital U with a subscript of C, which is 1/2 times our capacitance times delta V. So 1/2 times 150 times 10 to the minus 6 farads times delta V, which is 2100 volts. And that gives us a capacitance, or an energy, of 331 joules. And then our energy density is a lowercase u with a subscript of E, which is our energy, divided by the area between the volume between those plates, which is area times distance between the plates. 331 joules divided by the area, 2.82 meters squared, times our distance, gives us an energy density of 2.35 times 10 to the 6 joules per cubic meter. That's a lot of energy. Okay, so let's go on. Let's come back to that question. How on earth do they make the capacitor with such a big area? Well, what they do is you take your capacitor plates. I've just got a model here. I cut 2 sheets of a roll of aluminum foil. Then what you do is you place your dielectric between the sheets. The dielectric between the sheets has got the advantage that it lets those plates go really, really close, but it doesn't touch. And then we'll just put another dielectric right on top of that, and then we roll it up. So right now, I've got a pretty big area, but if I roll it, this is a little bit hard to do. If I roll it up tight, and of course if I were a technician making a proper capacitor, I would do a better job. You see now all of a sudden this is a lot smaller. So practically this is how they actually make capacitors with dielectrics, to give them a large area that don't actually take up a lot of space.